screen and hear me. So this is a continuation of the talk that just finished. Whereas in that talk, we were describing these model interfaces from more of a generic perspective and trying to think about what these various classes and methods within them might do just by sort of looking at the interfaces and thinking about, what those interfaces imply. Here, we're actually going to show how they're implemented for a specific model. So if you were doing this in practice, if you were trying to write a new model interface, you would probably want to follow one of the existing examples as opposed to starting from scratch. And there are various examples now which I'll go into during this presentation. So the outline of this talk is just to give a brief introduction and to outline what we'll be talking about. Then go back into these model space classes, but with examples of how they're implemented for a specific model. In this case, it's around the FE3 model, which is the model used by NASA for their GEOS system and NOAA for their UFS system. We'll talk especially in detail about the get values part of the code. Then we'll talk about how you actually build an application, because the interfaces for the model is where you actually build the applications as well as writing these interface classes. And then I won't present this, but the slides are included in case anybody is interested. They describe the linked lists, which is very detail oriented about how the mixed language approaches are handled in these model interfaces. Okay, so just to introduce things. So as we know, OOPS provides these algorithms that combine generic building blocks into applications. So these could be variational DA or forecast, ensemble applications, or forecast sensitivity applications like FSOI. By design, OOPS knows nothing about these actual implementations. So there are these, we saw in the last talk, there are these generic building blocks or interface classes. How they are implemented is up to the model, and OOPS will never know how that was done, and it keeps that separation of concerns. And these are it's the model space interface classes that have to be implemented. The other thing to note is that a lot of the time forecast models are not written in C++ like OOPS is. They're often written in Fortran. You're even seeing some models written in Python now. And so often a mixed language approach is required. And so there are these binding or sort of sub-interface layers, I guess you could call them, between the C++ and the Fortran. And as we build these interface classes and add them to the model interface, applications based on those building blocks become available. The other thing I guess I didn't note here, which I should note, is that the model interface also has to have lots of testing, which I'm not going to talk about in detail. There's going to be lectures on testing. But basically, as you build these interface classes and implement them in specific ways, it's crucial to make use of the testing of these interface classes in your model interface. And so I think Mariam's going to talk a lot more about how that all works tomorrow or Friday. So at this point, this may not even be a complete list. At this point, I probably should update this table. But at this point, there's quite a large number of models that have been interfaced to the JEDI system by people from different centers, actually all over the world now. So the UFS or GFS model has been interfaced, as has GEOS, the NASA model. There's also chemistry or aerosol versions of these NWP systems. There's a regional NWP version of FE3 working with FE3 JEDI now. There's also a regional air quality system. So all of those are based off of the FE3 model. The dynamical core in all of these systems is FE3, whether it's global or regional. And so they all use the same interface, the FE3 JEDI interface. And that's the one we're going to take examples from a lot of the time in this presentation today. There's also NCAR who are working on an interface to the MPAS, which is the MPAS model, atmospheric model, which is icosahedral grid model. FE3 is a CubeSphere grid, by the way. They're also working on an interface to the WRF model, which is a regional system. The Met Office in the UK is working on interfaces to ELFRIC, which is a CubeSphere system, as well as the UM, which is their current operational system, the unified model. At NOAA JCSDA and NOAA EMC are working on the SOCA interface, which is the sea ice ocean coupled assimilation interface. That has interface to the MOM6 ocean model, the SIS2 ice model, sea ice model, and then SIS6 sea ice model. The Naval Research Lab is working on the Neptune interface. Neptune is another CubeSphere model. And then we also have various toy models. So coming with OOPS itself, developed by ECMWF, is the QG model and the Lorenz 95. So they're actually shipping with OOPS and are there to make sure that all of the developments in OOPS work with at least these two models. And then in addition to that, NOAA has developed the shallow water model interface, which is basically another toy model, but a little bit more complicated than these two. So these are very useful for doing quick testing or running kind of data assimilation with research, like in academia or something. And then all of the rest of these are kind of like operational systems. Okay, so talk about the model space classes with examples. So here we're showing the same code snippet that we showed before. So this is the generic geometry class interface from OOPS. And so you can see what we saw just now, which is the interfaces for the constructors and destructors, the geometry iterator, and then the accessor functions. And then this was the specific implementation pointer that we saw. And then this is the same class, but now implemented for FE3. So, I mean, you actually don't see here that it's really FE3, but the namespace is FE3 if I showed more of the code here. So this is all pseudocode. It's not necessarily what you'll see if you go look in the files. It's sort of cut down a little bit just to make it friendly for a presentation, but it gives you hopefully a sense of how it all works. So again, you just sort of, you have basically the same interfaces, but now instead of this geometry underscore, you have the actual geometry class, which is the class that we're working with in here. Same with these geometry iterators. You see we drop the underscores. So it looks very similar down to about here, and then you'll see this F90 geom. So that's results from the fact that the underlying model is a Fortran based model. So this indicates the binding between the Fortran and C++. These are essentially integers, but given a special kind, so they don't get muddled up with each other. And it's essentially a way of bookkeeping to make sure that the Fortran version of the object is equivalent to the C++ version of the object. And like I said, you can look at the linked list part of the talk at the end if you're interested in knowing more about how that works. And then you'll see these private data members, which are basically just things that might be specific to this implementation. Okay, so here's an example of that constructor, again, pseudocode. And there's two examples here. The first one is if you were to have a C++ based model. So basically you didn't need to do anything in Fortran. So coming in here is the configuration and the communicator. You make a local copy of the communicator just to keep track of it. And then you basically kind of have this pointer to the config so that you can actually try to read it, because otherwise you just have a reference to where it is in memory. And this is a very simple example and not realistic at all. But let's say for your geometry, in order to allocate your states and increments, all you needed to know was dx and dy. Then you would just get from the config dx and dy, and you'd put them into these local variables dx and dy. And that would be basically all you needed to do. Probably you'd need to do more and realistically create some lon lats or whatever. But you can basically just work in the C++. If you have a Fortran model, which is more common, it's the same interface, of course, you don't control that. But then what you do inside changes. So now instead of working here with the config, what you're basically going to do is pass them down into this interface. And then eventually this will come down into some Fortran where you can actually work with these data structures, but at the Fortran level. So you pass down this key, which we talked about. So that's this sort of bookkeeping thing, which keeps track of different objects that live at C++ and Fortran. And then you pass down the config and the communicator. So in terms of binding between the C++ and the Fortran, so basically originally you have the state.h interface class from OOPS. And then via these traits, you're going to implement that class over here in your model, which is in green. And so you have the header defining all the interfaces again, but then you also have the CC file, which is what we were just looking at on this last slide. So this would be in the CC file. So that's your implementation of the method. So then if what you need to do is get to Fortran, then you basically add this interface layer. So you have a C++ version, and then you have a Fortran version too. And so these two pieces of code will just take care of passing all the data from the C++ to eventually get to this Fortran layer here. And so I show you this not because I expect you to understand what's happening in these files, but because when you start looking at the source code, you're going to see all these files in the directory and probably wonder what they are. But the truth is you don't really need to actually worry about anything except this file, this last file over here, because this is where all the work can take place. And when you're working in here, you're not going to see any C++. It's all kind of hidden away at these layers here. The only exception to that would be if the interface changed. So if you were making a change where you realized you needed to pass an extra object or variable into the geometry, one of the geometry methods, then you would have to update these other files to update that interface. But otherwise, if you're just changing something about the way the geometry functions, you can just work down here in the Fortran and not worry too much about any of this. Okay, so in terms of the order of development, so if you're developing your own model interface, excuse me, you would probably start by implementing the geometry, and that would probably interact with your actual forecast model, unless it's a very simple geometry. But typically you'll need to call some method inside here, which knows how to create a cube sphere grid or an icosahedral grid, whatever it might be. And that would not be code you'd want to replicate down in here. Once you've generated your geometry, you would add a test to make sure the geometry is working properly. And then you'd go ahead and add your state and increment classes. So for both of these things require the geometry, as we saw in the interfaces. In order to have a state constructor, you would pass in a geometry, for example, as well as various other things. There's probably some overlap between these two, but you would implement them anyway. And then they're going to interact with each other as well through, you might diff two states to create an increment, for example. Once you have your state class developed, you could work on the get values. And then, like I said in the last talk, at that point, you would have sufficient work done to, say, implement an h of x application. So for each of these classes, you would implement all of the testing, make sure that each class is behaving as it's expected to, and then you would build an application and add an application test. Once you have the get values, you might add the linear get values, which would give you 3D var. Then you might add the forecast model to get 4D of x or 3D FCAT, and then the linear model, and then the variable changes, which would let you do more complicated things like, use the Poisson solver to use sine chi variables in your B matrix or something like that, or just to make things a lot more efficient. So that's the sort of the bulk of what you need to work on and the general order that you might work on it in. So here's what the geometry looks like when you've actually started to implement it. So this is taken from FE3 JEDI. So you'll see that basically we have a type here. So that mimics the class in C++. The methods are the same, constructors are called create, destructors are called delete typically, and then the copy constructor is called clone. So in C++, you don't really have to kind of define these or name them exactly. There's sort of default ways of describing constructors and destructors, but in Fortran you do have to actually sort of give them names like this. This is a slimmed down example, but basically you might have things like the number of grid points or the domain decomposition, the processor layouts, and then the lats and lons of the grid. And then as I said before, once you come down into this Fortran file, you don't see any evidence of C++. So it's the same interface, and it's designed to be the same interface as the C++, so it's very clear what's happening. But you'll see that the config and communicator now, which are the things that are passed in through that interface, are completely Fortran. So they're now, I guess, Fortran APIs, you would call this, to a C++ data structure, which is the config. So at this point, this config is the YAML file basically, and then this is the communicator that this geometry is going to be created for. So then you can get things out of this configuration using this API, get the communicator using this API, and you can create your geometry inside this self type. And you don't need to worry about the fact that this is being called from C++ or part of some big application. All you need to do is say, what do I need to get from this config to make put the right things in these variables. So the same with the clone, it's the same interface as in the C++. You have a geometry coming in, and you're going to fill up your current geometry with the information that came from the other one. Okay, so now onto the state and increment, which would be the next thing you implement. So as I mentioned before, the state and increment basically contains all the fields necessary to do data assimilation. So the state would be things like the background or the model state or the analysis. And then the increment would be perturbations of the fields. So, if you're doing like an incremental variational data assimilation, you would have the increment as part of, when you're minimizing, it's the increment that you're using in that algorithm. And as I mentioned, there's a lot of overlap between the state and the increment, which is represented in this Venn diagram here. So the increment has a whole bunch of methods that we talked a little bit about in the last talk. And then the state has a couple of methods that only the state has. And then both state and increment all have these methods here in the middle. So the constructors, both of them have the same basic constructors. The need to make copies or zero everything, all the data to zero, compute the norms, change the resolutions, et cetera, et cetera. So typically what happens is that we implement a so-called fields class. So if you look in, say, the QG model or the L95 model in OOPS, you're going to see this fields class, which you won't see in the interface classes. So it's not technically an interface class, just the state and increment is. You'll often see reference to this fields thing inside the models. And if you're not sure what that is, just remember that it's basically a way of eliminating the need to duplicate all of this between these two classes. So in FE3 JEDI, we did this at the Fortran level. So we create basically a base class called fields, and then state and increment will be extensions of this fields class. So just to give you an example of the kinds of things you need in here. So we have some copies of the geometry just for convenience purposes. We have some information about the number of fields, the date time information. We have a copy of the communicator just for convenience. And then what we have here is basically an array of another type with field singular. And then there are all these methods, which are the ones that are common between state and increment. The field type here, which contains the actual data. So there's an array of this, depending on how many fields need to be allocated. So this will have metadata in it, like names or units, whether it's a tracer, what stagger, whether it's a staggered variable or not, and then the actual data, which would live in this array down here. So then, as I said, the state class and the increment class just extend the field and then add the methods that only that one needs. So you could just do this at the C++ level, and it would probably eliminate some of the interface code that's sort of duplicate between the two. But one of the advantages to doing it in the Fortran level is if you're primarily working in Fortran, then you always know if you're dealing with a state or an increment. Whereas if you do it at the C++ level, everything's called a field and it's not always exactly clear. But there's pros and cons to both, and it doesn't really matter at the end of the day whether you do this at the C++ level or the Fortran level. In FE3 JEDI, we have something called fields metadata. So basically, we don't have any fields referenced in the source code, just to keep things flexible and make it easy for people to add new fields where, as different applications come along. So for example, we have some aerosol chemistry applications where there's something like 200 fields in the background. And so we don't want to have to write those all into the source code. So what we do is we use this thing called a fields metadata class. And then we have a YAML file, which basically defines all the fields that the system is capable of allocating. And it does this using a map in C++. And basically it connects the potential field IO names, which could be multiple, with a certain set of metadata. And so if you want to add a new variable to the system, you basically go into this YAML and add the variable in the YAML. And you don't have to change the source code. So here's an example of allocating a field. So first thing we do is get the field metadata using the Fortran API. So here we're saying, okay, give me the U variable. Of course, in reality, you probably iterate over some list of variables that comes in. But here we're saying U, which means that we'll come along here and using the map, basically find this metadata for U. So this could also be UD or U, lowercase u. And then you can see, like, from this metadata, we know that, okay, this has a stagger location of north-south on the grid. So we can allocate it with the extra grid point to take care of that staggering. Then in the YAML file, which you would have seen in some of the tutorials, is just specifying a list of variables. So the user here picks the variables that they expect to see in their files. So I think GFS uses ice water, but GEOS uses QI, but it will get the same metadata because of the fact that you can have multiple kind of items in the list here. So as far as the user's concerned, they just work with the variables as they're named in their files. And then if you're working with the field internally into the source code, you would use the sort of fixed name, in this case, UD or VD. So inside the code itself, if you want to access a field and manipulate it somehow or get the data out and use it for something, we have these accessor functions. So we can basically check whether a field is allocated and then have various different structures or ways of getting the data out. So we can get a pointer to the array, we can get a copy of the array, or we can get a pointer to the actual type with all the metadata and everything else. Okay, so here's an example of a method in the increment class. So this is the share product. So you have self, which is the increment of the class, and then the one that's coming in, which we've called right-hand side. And so basically in this method, you have to compute the share product between these two increments. So you can optionally check that they both have the same set of fields, which they would need to have in this case. But it's just for being extra cautious, I suppose. And then you basically just loop over all the fields that happen to be allocated for these two increments and then compute the share product by multiplying element by element in that method. So you can see there's no reference to any specific variables. You just loop over everything that's allocated. So the next thing we'll talk about is the forecast model. So all the algorithms in JEDI are designed to work with the model the way we described it in the previous talk with the forecast method and the step, initialize and finalize. But of course, those need to be implemented. And I'd say this is one of the hardest parts of the sort of interfacing work, because very often you're dealing with a quite mature model like UFS or GEOS or something like that. And they're seldom designed with their interfaces exposed to an external driver. They sort of design them with a driver sort of included with them. And so some work is often required to actually be able to drive those models from the external system of JEDI. It's also necessary to be able to rewind the model if you want to do outer loops and change the internal states. And that often requires some work inside the model. It's not something you can really take care of from the outside. So you need some collaboration with the model developers in order to be able to do that for these complex models. But I would say there is definite potential benefit to running in core. First of all, it definitely simplifies the workflow. If you can just do the forecast and the assimilation in a single step. And it has major potential efficiency benefits. Like if you're doing 4D var with multiple outer loops, the cost of going in and out of these executables and reading and writing all the states from disk is definitely very high. So huge potential benefit and potential to open applications that otherwise wouldn't be possible, such as 4D var. So this is what the implementation for GEOS looks like. So we've talked a little bit about traits. So this is actually all the models, as well as the variable changes actually are handled through factories instead. And that means that you can implement multiple versions of the same class. So with geometry, you can't have multiple different geometries in the same interface very easily. But here with the models, you can have GEOS, you can have UFS, or pseudo model, or as many as you want really. And then you can basically put them together using this factory. So if they didn't have the same modules underneath, you could compile GEOS and UFS in the same executable if you wanted. So into this interface is the resolution and the configuration. So you'll create the model based on that configuration. For GEOS, same as UFS and same as I think most like realistic NWP models, you have to be able to run the executable from a certain directory where it expects to see various files. And so in this case for GEOS, we actually move to the directory that the config tells us to move to, which is this GEOS scratch directory. And then we call the Fortran part of the code once we've moved into the correct directory. And that's quite useful to be able to do for some of these models. And then once we're down in there, we can allocate the model as we normally would. So here's 3 examples of the models we have in FE3 JEDI. So we have the GEOS model, the UFS model, and the pseudo model. We also have a standalone FE3 dynamical core as well, but I'm not showing that here. The only point I want to just kind of bring home from this is basically that often these model structures are sort of encapsulated in a single object. So this maple type, for example, maple cap type here, that's the entire GEOS model, and we just basically drive the model and access all of its states via that function. Sometimes there's a few extra things that you need. So we have these information here to basically tell it whether we need to rewind the model in order to do a second outer loop or a second forecast. And then, some information about whether the internal model states have been saved correctly. Same for UFS, there's just this sort of UFS driver that basically encapsulates the entire model. And it shows you the methods at the Fortran level for these. For the pseudo model, you're just reading stuff from disk. So you don't actually have to interface to the entire model. You can just read those states at the correct time for that time step. And it would be the same as running the model in core, identically the same, except in 2 executables. The only difference is with the pseudo model, you can't do things like outer loops. One thing to note is sort of how the data flows in and out of the model. So for FE3 JEDI, there's an FE3 JEDI state, which comes into this step routine. So that's up here at the top. So that's the state that comes in. And then of course we want to advance this state by this model, and then, get the state back out and send it, back onto the next thing that's going to need it. But this FE3 JEDI state here is a different type, most likely, than what the model can interpret. So you can't just pass this thing, into the model, or at least not easily. You'd have to change the model to be able to do that. So there's usually essentially sort of a handoff between the state that comes in and then the actual internal model state. So we're showing this example for the standalone dynamical core. The state comes in, and then we basically fill up some internal model state with the variables. Then we can step the model, and then we basically exchange them back. And then once it's come back, then you can go off and call all of your post processors. It's very similar with the linear model. One thing to keep in mind about the linear model is it's run, if you're doing something like 4D var, then you would actually run your whole forecast every time you do an iteration of your minimization. So like yesterday, we were looking at examples with 25 iterations per outer loop. And so that would be 25 forecasts if you were doing a 4D var. So you do the create here, not once per executable, but once per outer loop. And then this set of routines, the forecast method, would be called essentially, as many times as it's needed for however many iterations you have. And then the Fortran methods just look like this, basically the same, but sort of appended with this TL or AD. Again, you have an exchange of data between. So this is next we'll talk about the variable changes. So this is that 4D var cost function again with lots of math, but doesn't really matter. The point here is just to highlight where you have these variable changes. So in a lot of applications, you need to, or you don't necessarily need to if the variables are the same, but in many cases it helps if you can use variable changes. So if we focus on this third line down here, so here we're computing departures, which is the difference between the observations, y, and h of x. So in 4D var, we start with the background, and we propagate that background out to the time of the observation, and then we call the observation operator. But throughout that process, the variables are changing. So over here, this x0 is the background variables, but the model might need a different set of variables than what's available from the background. So we have a variable change before we can call the model. Then in order to call the observation operator, h, we might need another variable change to get to the variables that h expects. So all throughout this system, there's lots of these variable changes. And we've implemented most of these now in the JEDI system. So there's a few different sets of these variables. So there's the background variables, the ones that basically read from some file and then used to create the increment, which is the analysis or increment variables. I think in the YAML, they're called analysis variables. So this is usually a subset of these background variables. Then there's the model variables, i.e. the ones that are needed to make a model forecast. Then there's linear model variables, which might be slightly different. Then the B matrix has different variables. Some people call this analysis variables. We call them, I guess, control variables or B matrix variables. And that would be things like psi and chi. And then there's also the observation operator variables, which are the ones that are needed to fill up this GFLs object. So this shows the nonlinear interface or class on the Fortran side, and then the linear version. So so here you might have some sort of saving of the grid just for convenience, and then your create, delete, and then your change var function. And then for the linear version, like for example, here we're saving some variables, T, Q, and ozone that would be needed as part of the trajectory in order to do some of these variable transforms. So we have multiply, adjoint, etc. And so these are the model to GEOS. So that's the transform that happens before calling the observation operator. On the C++ side, you can see just showing the interface here. and showing basically how these objects are created. So again, it's not using the traits, it's using a factory. So we have this maker var change model to GFLs. And so if you want to use this variable change, you would use the string here in the YAML file. And there's going to be some examples of that in the tutorial. Here's what the general structure of variable changes looks like in FE3 JEDI. So basically you have coming in here. So this is an example where you're converting from B matrix variables back to analysis variables or increment variables. And what you have coming in here is the X control or B matrix variables, and then the analysis variables coming out. So the first thing we do is copy any variables that exist in both. So the identity part of the variable transform, and then we return a list of the fields that we still need to transform. If there's nothing to do, we can just, if it's just an identity, we can return. Then what we basically do is we try to create the variables that we expect the outputs to need. So in this case, we expect to need the dgrid wins. So we set it to false. And then we check to see if we have psi and chi in the inputs. If we do, we can get them. And then we can convert psi and chi to the wins and then set the flag to true. Then basically we just loop over all the fields that we need to actually get. And then we have some predefined cases. And then as long as this is true, as in we've been able to create this variable, then we can basically put it back into the output. So this is the get values. So this is a pretty key part of the whole system. You really can't do anything without get values, and it's a little bit tricky to implement perhaps, certainly more tricky than just the state and increment. It helps to have a bit of an understanding of how it works too, and how it sort of fits into the algorithm. So basically, you have your model step that's going along, and after your model step, you have your state, which might be your, if this was your model variables, you know, the dgrid wins, temperature, pressure thickness, and moisture, say. And then basically what you're going to do is, OOPS is going to loop over all of the observation operators that have been requested in the YAML file. And then inside FE3 JEDI or the model interface, it basically has to try and get from these model variables to the GEOS. Okay, so this top row here is the CRTM. So we don't know it's the CRTM. All we know is that it's a list of variables that, you know, happens to be the CRTM variables, but we don't know that it's necessarily from the CRTM. So the first thing we do is do the variable change. So maybe it's asking us to give temperature, pressure, and some surface information. So we can do a variable change to go from model variables to these variables. Then we have another state. Then we can call get values, which produces the GFLs. And then when we go to the next observation operator in the list, we'll be given a different list of variables, in this case, UA, VA, T, and Q, which is the ones that the user has asked because they're trying to do aircraft. So we do a different variable change to get these variables, and then we can call get values and then fill up the GFLs. And then we just keep doing that for all of the different observation operators. So if you look in the get values code in FE3 JEDI, for example, you'll basically see this process happening there and inside that interface. Here's what the get values constructor looks like. So recall that it receives the geometry and locations. So we have to create an interpolation object to get from these grid points to these grid points, or these long lats to these long lats. So the geometry and locations, which actually a UFO quantity, come in. And then in this example here, we're just showing how to use the bump interpolation. So this is something that comes from the bump or Sabre background error model. And you just pass it the communicator, the size of the grid on that processor, and then the lons and lats, and then the lons and lats that go for the output side. And that's all you need to do there. And we provide a lot of these interpolation routines through Sabre and through OOPS that you can use in your get values. And then when you come to do the filling up of the GFLs, so now we have a state and 2 date times coming in, and we're going to fill the GFLs and pass them back. So that's what the interface looks like. So the first thing we do is we ask for a mask given these date times, because when we did when we constructed this interpolation object, it was for all locations throughout the whole window, not just not different sub windows or time sets, but the whole window this would be all the locations on this processor for the whole window. So first thing we have to do is get a mask, which tells us, you know, which of these locations that or which of these GeoVals, which correspond directly to locations, are valid between these two times, the time step of the model. Then we basically loop over all of the variables the GeoVals needs. We go get that variable from our fields. Then we basically just apply the interpolation routine that comes from bump, which will give us the GeoVals at all of the locations. And then we basically just use that time mask to fill up the actual GeoVals with the ones that are valid for this particular time window. And so that's it. It's actually fairly generic in some sense. It wouldn't be very hard to use it for a different model. If you added new variables, both to the UFO and to FE3 JEDI, this code would not change at all, provided that this, you know, interpolation would work for that kind of field. The final section is just about how to build an application. So the model interface is where you build applications like the variational DA or the forecast or H of X applications. So basically you have all of your classes that you've now implemented, plus actually I guess UFO has its own traits now, so that should not be there, that yellow box. I need to update that slide. These are all handed off through these traits, or in some cases factories. And then you basically have a driver, sort of an application that's model specific, which connects up to the application through OOPS, and then basically gives you an executable to run. So OOPS on its own is just sort of headers and kind of doesn't really compile, I guess. It's not until an actual application comes along and then you actually go ahead and compile all those header files and put together an actual application. This is what the traits look like for the model. So you see, we have like our own version of error covariance, although it doesn't really do anything because we just use the one from Sabre. But then we have, you know, increment geometry, get values, linear get values, the state, and the model bias ones, the model auxiliary ones. You'll notice that we don't see the model, the linear model, or any of the variable changes, and that's because they come through factories instead of through the traits. So here's what the application driver would look like. So this is FE3 JEDI var. So this basically creates the variational application for FE3. So it grabs these traits and then it grabs the factories. So there's two different ways of doing factories. You can have these instantiate factory files, which is what's done in Sabre, and also in, I think UFO does the same with like the filter factory. In FE3 JEDI, there aren't these files. We just add that kind of variable to each individual piece of source code. So they're kind of created as it compiles them, and there's not this additional file. And then you get the traits from UFO because it has its own traits. And then you actually include the application that you want to build from OOPS. Then you'll see the interface here. So it's the main driver. And then what's coming in here basically is the YAML configuration file. Then you basically create your run object. You instantiate all these factories, which basically goes ahead and allocates all of those different objects. And then you create the actual application object, in this case, the variational, and then you execute the application. So that will then run the whole variational system. And as I said, there's additional backup slides about the binding if you're interested, but I'll leave it there and take any questions if there are any questions.